Hello, and welcome to our next Chem Honors lesson, continuing with our study of acids and bases. Today we're going to look at some simple properties, some physical and chemical properties of acids and bases. I guess actually they're all chemical properties. Sorry about that. And explore the second model of acids and bases that I mentioned the other day in the notes. So, just a few simple properties that I want you to remember, to know about. As we talked about the other day, acids are going to be polar covalent molecules, and they're going to have that H plus, that hydrogen ion that can be removed. And it's usually written first, as in, say, HCl, or you can write it at the end. And we saw that with acetic acid, CH3COOH, and that's far from the only one that does it. There's a whole family of those acids, and we'll see more about them in the next lesson on strong and weak acids. Acids always have a sour taste, so think about lemons and citric acid and vinegar, which came from the French word for vinaigre, and I'm sorry, I know I probably slaughtered that word, which means sour wine. So the sour taste indicates an acid. Acids also change the colors of acid-base indicators. Excuse me, we'll talk more about those later on. Excuse me, when we talk about acid-base indicators. And as we saw, they are also electrolytes. A couple of key chemical properties we've seen before. They react with certain metals to release hydrogen gas, and this is a single replacement reaction. And there's our hydrogen gas. That hydrogen gas did come from the H plus of the HCl, and we've talked about oxidation reduction reactions. This is an oxidation reduction reaction as well, and we'll talk more about those in electrochemistry in the next unit. They do react with carbonate ion, and hydrogen carbonate, and they form carbon dioxide. So sodium carbonate reacts with HCl, and we're going to get some carbon dioxide gas coming out of here. If we have sodium bicarbonate, HCO3 used to be called bicarbonate, then we have the classic vinegar and baking soda volcano that you may have made at some point in the past. They react with acids and bases. They react with bases to form water and salt. This is a neutralization reaction. We saw a bit about these back in our unit on solutions and solution stoichiometry. And the H and the hydroxide from the base come together to form water, and then the other ions come together to form a salt. And again, we'll talk more about these when we talk about titrations and neutralization reactions. Bases, on the other hand, are bitter taste. So bitter herbs, bitter vegetables, those are all alkaloids, which is a kind of base. They have a slippery feel. Their aqueous solution has a slippery, soapy feel to them, and that's one way of differentiating. They change colors in acid-base indicators again. They're an electrolyte. Oh, and I didn't mention this up above. Corrosive to skin tissue. Acids are also corrosive to skin tissue. I'm not sure why that's not up there. So the two models that we're going to be focusing on in this class, there's a third, but it's not that important to us, is, as I said, the Arrhenius model, which we reviewed, which we did yesterday or the previous day in notes 15.1. And go back and review those, but just to refresh your memory, acids give us H plus in water, and bases give us hydroxide in water. And you can see those ions in the formula for the acid and the base. The next model, called the Bronsted-Lowry model, or sometimes just the Bronsted model of acids and bases, BL if you want for short, focus is not on what happens in water, because we can have reactions that don't take place in water, although most of our reactions will. We can have reactions that don't use water, don't have water as part of them, and that's something that doesn't happen in the Arrhenius model. Now we're going to focus on the H plus ion. And the H plus ion, scientists, chemists have been calling a proton. And what happens is the acid donates or transfers that proton, and it transfers it to the base. All right, so the base accepts the proton. So in this reaction down below, we've got the HCl gas coming in, we've got the water there. Now, unlike the previous day, I actually have water written in as part of the reaction, and you'll see why in a moment. Now, when we have this transfer, I want you to indicate the transfer by taking that proton and recognizing that the HCl is the acid. So let's label this down below that this is the acid, and it's going to transfer its proton to the water. Now, remember, water had those lone pairs. High electron density is going to be attractive to the lone proton. Remember, proton is just a single proton. A hydrogen ion that doesn't have an electron has nothing but a proton in it. So we transfer to the water, and what we end up making is that hydronium ion, H3O plus, and we'll talk about what its role is in a few minutes. At the same time, we're going to take the water. Now, water is accepting a proton here, so water is acting as a base in this reaction. And when the hydrogen ion comes off of the HCl, it leaves behind the chloride ion. And again, we'll talk about its role in a few minutes. In these Bronsted acid-base reactions, we always have to have one acid and one base, because something has to give a proton, and if something gives up a proton, something has to gain that proton, something has to accept or get that proton that was given up. So this is different from the Arrhenius model for acids only in the fact that we're now specifying where that particular proton is going, not just that it gives it to the water, but we're specifying where it goes. For bases, we get a different model. So you can see that the OH minus in a base for a Bronsted-Lowry base has the ability to accept a proton, but we'll get back to that in a few minutes. Now we're going to look at how a base differs specifically in the Bronsted-Lowry model from the Arrhenius model. So NH3, ammonia, is a Bronsted base, but it's not an Arrhenius base because it has no OH minus in it. There's no hydroxide in the formula. So how does this work in terms of proton exchange? So down below now I've got our chemical equation, ammonia and water. Again, for these reactions, we always have to have an acid and a base present. So you're always going to have two reactants. And we have water written not as H2O now, as HOH, because I want to specify that one of those protons down below in this structural model of the reaction is going to be pulled off of the water by the ammonia. And again, remember, ammonia, the nitrogen has that lone pair up on top. So we're going to take that proton, and that proton is going to be attracted to the ammonia. When it does, now ammonia, let's label ammonia as the base. And since ammonia is the base, water is now acting as the acid. And we'll talk about what that means for water in a couple of minutes. When that proton comes onto the ammonia, it now becomes ammonium, NH4 plus. And so it now has, let's draw that structure down below. It's this tetrahedral. I believe we saw ammonium in our studies of Lewis structures. So it now becomes the ammonium ion. And notice that when you split that water apart, so when you take that H off of the water, what's left over, and we saw this yesterday as well, is the hydroxide. And so let's draw that formula as well. So we have an acid and a base in our reactants, and we're forming the ammonium ion and the hydroxide ion. In fact, any compound that has nitrogen, that has 3 bonds to it, and that lone pair can act as a base. And to the right here, I've drawn the structure. This is a compound called ethylamine. The amine means nitrogen. And notice it has that same kind of structure as ammonia. It's just got this CH3 in place of an N. I'm sorry, in place of an H. And there are many different examples of these. All of these guys are weak bases because their reaction does not go. Remember, the reaction is less than 100%. So we don't form that many ions. These were the dim light bulbs in the conductivity test. So weak base, and we'll talk more about, again, weak acids and weak bases in the next lesson, exactly how those play into equilibrium. Now, water itself has some unique properties, and in the lesson that follows next lesson, we're going to look at some of the properties of water and see exactly where we get pH from. H2O has a property that's called amphoteric, AMPHOTERIC, amphoteric. And this is a property of being able to act as either an acid or a base. And it's going to depend on the strength of the other compound. And so we'll see sometimes water acting as an acid, sometimes as a base. For the purposes of today's lesson and today's homework, it would be pretty obvious for you which one water is going to be acting as. I'm either going to pair it up with something that's either obviously an acid or obviously a base, or in the homework, I'm going to give you some products, and you're going to see that either the water has gained or lost a proton to form hydroxide or hydronium ion. Now, in this model, we do have names for the products as well. So up above, you notice I drew the products in a certain color, depending on what kind of compound they actually are. In this model, the products are called conjugates. And conjugate can be an acid or it can be a base. And they, together with the reactant that they came from, they constitute conjugate acid base pairs. So they always come in pairs, conjugate acid base pairs that exists on opposite sides of the reaction. The conjugate acid is formed when the base gains a proton. They always differ. The conjugate acid differs from its base. So we'll have a conjugate acid and base. The conjugate acid always has one more proton, and so it has one more H, and it has one more positive charge. The conjugate base is formed, Cb, conjugate base, Let's see, so conjugate acid and conjugate base up above. Conjugate base is formed when the acid, so it always comes from the opposite. The acid loses a proton. And so we'll see that the base is always going to be down one proton and down one charge. So let's write this up. Up one H and up one positive charge, down one H and down one positive charge. Now, down to positive charge may be either going neutral or getting negative. Going up may be becoming neutral if you start negative, or becoming positive. So, for example, the conjugate acid of water. If we assume water is a base, so label water as a base in this case. That rhymed, right? The conjugate acid of the base, we lose a proton, and you lose a positive charge. So we go down from H2O to OH, go from neutral to -1. So, I'm sorry, I'm going backwards. My bad. Conjugate base, we're gaining a proton. Conjugate acid, we're gaining a proton. And so we're making 3 protons, 3 H's, H3O plus. And notice that we have that up above in the first reaction with the HCl. So the H3O plus is our conjugate acid. Meanwhile, we started with the acid HCl. So that was our acid. And when that HCl loses a proton, so get rid of that proton, we're left with Cl minus, the chloride ion. And so that's the conjugate base of HCl. So again, let's join that line here, coming up to this reaction. Now we can label the Cl minus up above as the conjugate base. So notice that in these reactions, we're going to have an acid and a base on both sides of the reaction. Now, this reaction does go 100%. This is a strong acid. I want to write 100%. And for this reason, we don't write these reactions as equilibrium. But if you were to think about a reverse reaction, think about what would happen, who would gain the proton, who would lose the proton. So in a reverse reaction, if we were to do this, and I'm not going to do this, it's going to write it in and I'm going to erase it so you don't think that it's something we want to always do. We'd notice that the acid would give to the base. As I've said, we don't want to do that because I don't want you to have to worry about what's going on in the products. We're only going to focus on transferring in the reactants. And in this particular case, there is no reverse reaction going on. However, in the next reaction, there is a reverse reaction going on, and we can talk more about how ammonium is going to work. So if we look at ammonia, which is the base, so ammonia was our base in the first reaction. Now, when we take that ammonia and we add a proton to it, so again, to make the conjugate acid, add the proton. Now we're going to make NH4 plus. By the way, in other compounds, in that ethylamine, if we take CH3 NH2, to add the proton to it, let's put that little plus a proton there. We're going to want to add that proton to a place where it can do acid-base chemistry, and that's not the CH3. First of all, think about the formula. So if we take the formula CH3, we're going to have something that looks like, let's see, NH2, CH3. There's no place on that carbon to put a proton, but there is a place on the nitrogen to put a proton. And so when we have these guys, we're always going to add the proton to the nitrogen and make CH3NH3 plus. don't make it CH4NH2+. Okay, so the conjugate base of ammonia is ammonium. And now we see the relationship. Maybe you've thought about it. Is there a relationship? Ammonia, ammonium sound very similar. And here's the relationship. So now ammonium is the conjugate acid of ammonia. And hydroxide then is going to be the conjugate base when that acid water loses its proton. And so we can label in this reaction the conjugate base. Okay, so we always have a conjugate acid, conjugate base. You don't need to have the reaction to know what the conjugate acid, conjugate base is. If we look at acetic acid, and I've written it this way, HC2H3O2, the conjugate base is always going to take that proton. So there's our acid. We're going to take that proton and remove it, and so the conjugate base is going to be C2H3O2 minus, or, sorry about that, or we can also write it CH3COO minus, where that H at the end of the COOH has come off. For carbonate ion, carbonate is a base. So how do you know it's a base looking at this particular compound? It's a base because there's no proton in there. It can't donate a proton, so it's going to accept a proton, and the proton is actually going to go onto one of the oxygen atoms. And so when we write the conjugate acid of the carbonate, now we don't write it on the proton. Now I told you up above, write it on the nitrogen. Here, for convenience sake, we write, I didn't want orange. Let's go to red. I thought I picked red. HCO3 minus. You're never going to see it the other way. When we talk about weak acids and bases, I'll show you a couple of alternate ways of writing several of the different weak acids and bases. The HCO3 minus is the conjugate acid. It can also accept a proton, which makes it also a base, still a base. And so this is another one of those things that can be amphoteric. Oh, and that reaction was supposed to be, I should have checked, was supposed to be on the first page. It probably will be for you guys. So I just told you about acetic acid. This guy, this acid on the left, I've got it labeled for you. This acid is not acetic acid. This is propionic or propanoic acid. Prop meaning we got 3 carbons in there. So propanoic acid and sulfite, SO3 minus sulfite. And I've told you that it's an acid, so you know that the proton here is going to be transferred over to the sulfite. Sulfite then, oh, what happened to my circle? It disappeared. I like it when that happens. So the sulfite then is the base. In the products, you should have written H5O2 minus. That's the propionate or propionate anion. Again, don't worry about the names. And that's our conjugate base because the acid has lost its proton. And the conjugate acid then is going to be the hydrogen sulfite ion, where the base has gained a proton. So in the homework, you'll be practicing a bunch of these reactions. In some of the reactions, I will give you the entire reaction, and you'll have to just figure out. You'll have to label everything: acid, base, conjugate acid, and conjugate base. All right, finally, acids can be characterized by the number of protons or the number of H pluses in them. So they be characterized as being either mono, di, or triprotic. That's the highest we're going to go, is triprotic. We're never going to have more than 3 protons that can come off. So phosphoric acid has H3PO4. These always occur one proton at a time. And again, we'll see some of this when we talk about weak acids and weak bases. These are all, except for one of them, all going to be weak acids. So phosphoric acid is a weak acid. And they all have this equilibrium. And so they all occur one step at a time. This is going to be a stoichiometry kind of thing, where stoichiometry for these reactions is always going to be 1-to-1. So phosphoric acid is the acid, which means, of course, that water is going to be the base. And when we write the products here, we're going to write, I'm going to put the H3O plus first because I want to focus on something with the conjugate base in a moment. So the H3O plus, let's take that one proton and come on over. H3O plus, so we make our conjugate acid. And our conjugate base then is going to be H2. We've lost a proton, PO4, 2 minus. We lost a proton, I'm sorry, 2 minus, single minus. We lost a proton and we went down a charge that went down positive 1 or went down 1 in its charge. And so now we have the H2PO4. Now notice that in the next reaction, we're going to take that H2PO4. It still has 2 protons on it, so it can come down here as a reactant. Now in the first reaction, it is the conjugate base. In this second reaction, it is the acid. And so the same compound can act as an acid and a base. And I hope you recall, we call that H2PO4 minus amphoteric. So in all of these reactions, it's almost like an intermediate in a reaction mechanism going from the start to what you'll see is the finish in a few moments. That acid can then react with the water, and it's going to form another H3O plus. And its conjugate base is now going to be down 1 proton, and we're going to be down to, instead of dihydrogen phosphate, monohydrogen phosphate, or just hydrogen phosphate. And that's also, 2 minus, that's also an amphoteric compound. And finally, take that HPO4 minus, it becomes the acid in the third step of we call it a deprotonization, deprotonating these guys. And we make one more H3O plus. So notice we make the same number, in the end, we make the same number of hydronium ions as we started with hydrogen ions. And finally, we end this with the PO4 3 minus, the phosphate anion, and that is only a base. These are all conjugate bases over here. That's only the base. There's no proton left, so it can't further deprotonate. It can only act as a base. All right, so that is our lesson for today. Hopefully the homework is going to be relatively straightforward for you, and I will see you next time in class. Take care.